All right, so for 8.3, we are looking at conditional probability, okay? So the whole idea of conditional probability, it kind of has a different notation with a line like this, right? So it's A, B. So the wording is given. So the probability of A given B has happened. So like, what's the probability that you're going to commit a crime given you've already been convicted before of a crime, right? So that's like the kind of places that we're going to look at. So this word is given in a lot of the word problems, okay? So what it means is you take the probability of where they're both at, where they intersect, that and, because that's our symbol for and, right? The intersection, both where they both are, and you divide it by the probability of the second one. So if you went the other way, right, then you have to divide by the probability of the A. So it's the second one you're dividing, okay? Then the product rule that they say here is basically you can times different probabilities by each other. And we'll kind of look at that one individually. I don't know if I like that one super well, the way they have it kind of worded there, but let's look through examples. I really like this given probability or these conditional, because to me it's way more realistic in the real world than it is any other probability we really do. Okay, so this first question says, what's the probability of C? Okay, so the probability of C, here's our totals, right? There's 0.36. So our probability is 0.36 for this one. And notice this one adds to 1 and has all of our, we already have our decimals in here. It'd be a little bit different if they were counts. If we just had numbers we counted in here, you would have to add up how many counts are in C over the total. But it's like they already did that part for us. So this answer is just 0.36, adding those up. Okay, so for this next one, what's the probability of F? Okay, so here's our F is going this way, and they all add to 0.8. So our probability of F is 0.8. Okay, so for 3, we have an intersection. So what's the probability of being A and F, or where do they intersect, right? So A and F is this one at 0.05. This is where they both intersect right there. So this is equal to 0.05. And again, if it was counts, you would put that count, that however many were in there, divided by the total. Okay, 4, what's the probability of C intersection E? Okay, so C intersection, oops. There we go. C intersection E, so C and E is the 0.06. Okay, so that's this one, C and E. Okay, so that one is going to be 0.06. Okay, so now we have our first one for 5 that is A given F. What's the probability of A given F? Is kind of how we're going to say that. So where is A and F intersect? A and F intersects here. Okay, so that's going to be your top number, 0.05, and F, the total of F, the 0.8 for the totals of F, is going to be your denominator. Okay, so where they intersect, I got to erase that each time so we can kind of see. There we go. So it's the 0.05 of the A and F. So A and F intersect here, and then you divide it by the total. Now, if it went the other way, it's the numerator stays the same. F and A still intersect at 0.05. And now then the total would now be the totals of A, which is this one. So that's 0.07. Now we need to divide these because we don't like to see a fraction like that a decimal and a fraction. So I'm going to get out my calculator. 0.05 divided by 0.8 is going to give me, this one will end up being 0.0625. Okay. And 0.05 divided by 0.07. This one is 0.7143. I'll just go, oops, delete 3. Was trying to draw a triangle in the middle of my writing there. Okay, so 7, D given E. All right, let me erase these ones here. So D given E, so probability of D is the 0.39. So, oops, probability of D, what am I doing? Probability of D given E, 0.04. I was like, that's not right, 0.04, where they both intersect, divided by E. Now I need the total for E, which is 0.2. So 0.04, divide that by 0.2, and I got a total of 0.2. So the full answer is 0.2. All right, so E given B. So where is E and B? So E and B intersect here, and then total of B for that one. So that would be our intersect at 0.08, and 0.18 is the denominator. So 0.08, divide that by 0.18. I get 0.444 repeating forever. Okay, so 9, C given C. What is the probability of C something, right? Given you have that something. It's going to be 1. So it's going to happen, C given C. So C intersects with C at 0.36 divided by 0.36. Probability of C given C is going to be 1. So if they're the same thing, the probability is 100%. So what's the probability that you will pick an apple if you're going to pick an apple? 100%. That's a tricky one. Okay, refer to the table above. Are events C and E independent from each other? Why or why not? So are C and E independent from each other? So if we look up here, we're looking at C and E. Look, they have overlap. C and E have a place where they overlap. So when it says, are they independent? Well, the event of the first will not affine the other. So what's our rule for that? I think we could do it. I was like, well, I just thought it was, so the rule says, let's just write it out as their rule. I was going to say it a little different and I don't want to mess this up. So A intersect B has to equal P of A times P of B. So where's the intersection of C and E? So the intersection of C and E is 0.06. Does that equal the probability of A? Well, A is going to be our C. So the probability of C is 0.36. Oh, it moved. 0.36. And we're going to times that by the probability of the second one is E. So E is 0.2. So the intersection and the times, we want to see if those equal each other. So 0.36 times 0.2 is 0.072. So I got 0.06 equals 0.072. So no, they are not independent. We would say they're dependent. Really, they can't have overlap if they're independent from each other. Okay, B and F, let's check those. So B and F, B and F intersect at 0.1. So we'll have 0.1 equals the probability of B is 0.18 times that by the probability of F is 0.8. So 0.18 times 0.8 does not equal 0.144. So this one is also independent or dependent, excuse me. I'm looking at their key. Yeah, I don't know. This is dependent. They don't have one that's independent because those we don't have any non-overlap. So here's where I'm thinking. We don't have any with they having no intersection, like they all have values in here where they have intersection, like none of them are having a zero intersection. They're all kind of they're all dependent upon each other. So let's look at a different type of problem. 2 balls are drawn from a container that holds 5 red balls, 7 green, and 8 white. If the first ball is drawn is replaced before the second ball is drawn, find the following. So if you want the probability of 2, because we're doing 2, right? First and second, yep. The probability of 2 greens, you can do the probability of a green times the probability of a green. We can use that idea of times. So what's the probability of getting a green the first time is 7 out of what, 7? How many total are there? 8 plus 7 plus 5. I get 20 total. So there's 7 green out of 20, right? And think about if we're going to replace them, the second probability is still 7 out of 20. And these are independent of each other because one's not affecting the other if we put them back in. If we take a green out and leave it, or a ball out, doesn't matter what color, then that will affect our next time we reach in and pull one out. So that would become dependent if we have no replacement. If we replace, that's going to be independent of each other. So 7/20 times 7/20 is 49 over 400 or 0.1225. Taking these off their keys, so hopefully they times right because sometimes they have the wrong answers. I'm just assuming they did. So what's the probability that there is neither ball we reach in is green? Couple ways we could do this. So we could do all green and then, well, no, because that's not gonna in the mindset from 1, but neither ball is green. No, it's gonna be a little bit different. Okay, what's the probability that neither ball is green? So that's gonna be 13 out of the 20, right? And then the next one, because we're replacing them, is another 13 out of 20. Because there's 13 that aren't 7 and 13, right? Add to the 20. And this is going to equal 13 divided by 20 times itself is 0.4225. So I would have to do that neither ball is green. The reason I can't minus this one from 1 is because I'm not considering one ball being green. That would have to be added in here to get the -1. So we're not going to worry about that, but that at least one ball is green. So this one's more of what I was trying to think of for double I. So triple I, what weird, AB, should just have ABC, but at least one ball is green. So we would do, anytime we see at least, we want to do 1 minus none. So we want to do 1 minus the probability of no green for all at least 1. So 1 minus the probability of no green, which we already have. So it'd be 1 minus the 0.4225, and that's going to give me 0.5775. So at least we have to use the idea of 1. And why didn't that work up here is because this, I didn't consider the fact that you can get 1 green, right? This is the probability of 2 greens. You would have to look at all those different combinations. So the probability of no green and the probability of at least 1 are opposites of each other. None, at least 1. What, that the 2 balls are not the same color. So what is the probability that the 2 balls are not the same color? Oh, that's a lot of different combinations. So let's just think this through. We're going to have a red and no red. Isn't that what the color was? Red and no red, green and not green, and white and not white. So if we think about our first one, which would be probability of green times the probability of no green or not green, something else. So what's the probability of a green? Well, our green was 7/20, okay, and our not green is 13/20. That's our first one. Then we're going to add it to the next situation. So add it to the probability of a red and a not red. Probability of, oops, I should have my parentheses a little bit different, not red. Okay, so for that one, the probability of a red, I can't remember how many reds we had. 5, I think. 5 reds, yeah. So 5 out of 20, and then the other one would be 15 out of 20. Okay, the last one is white and not white. So we're going to add it to the probability of a white times the probability of no white, not white. Okay, so that's going to be a plus, and then we're going to have 8 whites. So 8, no, not 8 whites. Yeah, 8 whites. Yeah, 8 whites. So 8 out of 20, and then that would make 12 out of 20. So each situation had to be times together in order for us to get the probability of the 2 balls, right? Ball 1, ball 2, those have to be times. And that's its own probability, plus the next situation, plus the next situation. So that's an and an or all mixed together. And this type is really challenging to think through on your own. But we times 2 probabilities if we want them both, this one and this one. And we add them together if we want this one or this one, okay? If I put this all in my calculator, they say the answer is 0.655. So I'm just going to believe them because I don't want to put it in my calculator. Okay. Part B, if the first ball is drawn and it's not replaced, totally going to be different probabilities. Before the second ball is drawn, find the probabilities that they're both green. Well, think about this. I pulled in, I grabbed one. I have the full 7 out of 20 still in there, right? And we want both to be green. So the second one, when I times it by the second one, will be, well, there's only 6 green left because I pulled a green the first time and there's only 19 total. So you have to go down 1 on both because now you only have 6 green balls and you only have 19 left. And they say that this equals 0.11. Repeating. Okay, what's the probability that neither ball is green? So the first one, gosh, we have 2 situations though. So neither ball is green. So we have to look at red and white. Okay, so we think about the color red. There were 5 red. So that if we reach in and it's got 5 out of 20 for that first one. Okay, and then the second one The second one could be white. What about both white? No, not green. No, you would do 12. There's total 12 out of 19. Okay. I was trying to think through. Okay. So we reach in and we're pulling something out that's not green, right? So it could be a red, then it could be a white, right? This is representing a white ball. And then we're going to add that to what's another combination we could have. We could reach in and get the white first. So it's the full 20, 12 out of 20 for that, right? Because there was 12 white. No, there's 8 white. I think I'm thinking of this one different than they did. So they did 12 out of 19 because we have 5 red. What did I just say? We had 8. How many white balls do we have? 8 white. 8. So this is okay, 13 total, right? That's where they're thinking. There's a different way to think of this problem. I don't really like, I'm gonna go with what they show, but they are saying they're gonna reach in and get a red, and they could get a red or a white with the second one. Why are we not considering the white? Okay, I'm gonna go with what they have. So I'm gonna reach in, I pull a red out, so that's 5 out of 20, but I reach back in, I could get a red or a white, but one of those reds is taken care of, and we left it out, so that left 12. The second one would then be when I go to add them, right? Then it would be the probability of reaching in and getting a white, which was 8 out of 20, or 12 left out of 19 again. Neither ball is green because we could do red. We could reach in and get a white. Okay. 0.411 is the answer to that one. I'm second guessing theirs. If I come up with some another way to do it, I'll show it next time. I just feel like there's more than one way to do that problem, which I'm sure there is. So 3 dots, at least one ball is green, right? At least one, then I have to do the probability of no green. So it's going to be 1 minus no green. That's the only way to do at least. At least one, we have to do 1 minus. So this would be 1 minus the 0.411 that we got, which is 0.589, which, we just get that 0.411 from right here. Okay, that the 2 balls are not the same color. This one's going to be a little bit harder because we just have to count down. So if we reach in and we're like red and then just not red, right? Because this is the same one we did. So red, we have a probability of 5 out of 20. And then not red, we still have 15 left, right? That are not red out of now 19. So when we did this one before, we kept the 20s all the way across. Our second ones all have to become 19s. That's the only difference. So then we're going to add that. That was the red, right? Red. And then the next one we could do is our green, which is 7 out of 20. And then that's going to leave 13 left out of 19. And then you'd add it to 8 out of 20, and that would leave 12 out of 19. So it's going to be a little bit different, 0.689. And what did we get on the other one? 0.655. So it's a little bit more higher probability that you have 2 balls that are not the same color if you're going to leave one out. A little bit higher probability. Let's go to something totally different. A certain state is going to allow a person 3 tries to pass a written portion of a test to obtain a driver's license. If a person fails the test, he or she may retake the test a week later. If a person fails the written portion 3 times, he or she must wait a year from the date of the third try before they can try again. From past records, 80% pass the test on their first attempt. 20% pass on their second, and only 15% pass on their third attempt. Okay, what's the probability of passing a written portion of the driving test on the first or second attempt? So what's the probability of passing it on your first? So think about this. We want to think it's a little harder than it sounds. We have the probability of passing on the first attempt, which we like. We want that, right? Plus, you have the probability of failing your first attempt, right? Timesing by the probability of passing your second attempt. Okay, so this is your first attempt here. This is your second. This is your first. You have to think through. I think most people would forget that you failed the first one, and that probability is affecting overall. So if we go to put this together, what's the probability of our event, whatever, is what's the probability of passing the first one? 80. Plus, what's the probability of failing the first time? Well, if the probability of passing is 80, the probability of failing is 20. What's the probability of passing that second time? 20. Okay, so it's another 20. So let's times those and add. So 0.8 plus 0.2 times 0.2 is going to give me 0.84. So you have an 84%. And really, like, we could take the 0.2 times 0.2 and get 0.04. We can see that the probability of passing a second time is 0.2 for failing, 0.2 for passing. So you can get the 0.84. You could also do a tree diagram of this one and then times your tree probabilities, which I show for 8.4. That's kind of a sweet way to do it too. So for B, what is the probability of failing the test on the first attempt and the second attempt, but passing on the third? Ooh, so probability of failing on the first one is 0.2, right? What's the probability of failing on the second attempt? Well, passing's 20. So 80% chance you'll fail the second attempt. And then you're going to pass the third one. So that's the 3 together. So it's going to be fail, fail, pass is our probability. So it's like fail, fail, pass. Oh, that does not look very good, people. Pass your test on the first times. 0.8 times 0.15. I know on some exams after college, right, like to be in the medical field, like I know PA, you only get 3 attempts and that's it. So like if you can't pass those PA exams, I only know that because my husband's a PA, but and we knew that should be small, like 2% of the probability fail, fail, and then pass. Okay, so we can't just look at the 15%. We have to consider the first one, the second one, and then the third. Okay, what's the probability that a person will have to wait a full year? So fail, fail, fail. They're just going to be failing, failing. So first fail is only 20%. Second fail is 80%. And the third one is 85%. Really, it's not very likely you'll fail the first time. But if you fail the first time, your probability of passing the next one is still very low. This is why retakes are typically a waste of a teacher's time, because the student doesn't necessarily pass on a retake. They could, but okay, 0.8 times 0.85. All right, so I got 13%, 0.136. So 13% chance, almost 14% really, chance that you would fail, fail, fail. I like that question. Someone else might not like that question. don't love this next question as well. Give me 2 seconds. I'm gonna look and see if I have any other problems I want to show versus. Okay. This one just gave a table that's exactly like the first one. So I'm gonna just scroll down and do one that's slightly different. So this was problem, what, 14? Okay. So let's call this problem 15. So what if we had a spinner's probability? So here's our event, here's our probability. I'm going to give it to you in a table. So the event is rolling a 1 and you have a probability of 0.1. The event is rolling a 2 and you have a probability of 0.2. And a 3 is 0.1, and a 4 is 0.1, and a 5 is 0.3, and a 6 is 0.2. Okay, remember, for a probability table, these should add to 1, or it's not a probability table. Okay, so they have to add to 1. And what if I asked a question like, okay, what is the probability of landing on a prime? Probability of a prime. Okay, so the numbers that are prime, 1's not considered prime, which is kind of a trick. 2, 3, and 5 are prime, right? And if we want the probability of landing on a prime, it's like this one or this one or this one. So when we have or, we should think adding. Okay, so we would take our primes are right, 2, 3, and 5. Maybe you want to write that. So we got that from the 2, we have a 0.2. From the 3, we have a 0.1. And from the 5, we have a 0.3. So add those 3 up and I get 0.6. Okay, here comes a harder one. What's the probability of a prime? Prime, I forgot the R, prime, given you have an odd. So, right, prime given, you have an odd. So this is our conditional. We have to find where they both are, prime and odd, right? Where are they both located? So odds, just think of your odds, right, are going to be 1, 3, and 5. Those are odd numbers. So where are they both? They both will be where you have the 3 and the 5. So 2 of them overlap, the 3 and the 5. Okay. So I'm going to write this out a little different just so you have it for yourself. So prime, the probability of the 3 plus the probability of the 5 is where they both are. Then you divide it by the probability of the second one, which is our odd. So that would be the probability of the 1 plus the probability of the 3, because it's the odd plus the probability of the 5. So that's what it looks like in symbols. So if we went to put this together, it would be 0.1 plus 0.3 for the 3 and the 5 off of the table, and then the 1 is a 0.1 and the 3 is a 0.1 and the 5 is a 0.3. So I'm going to add that all up and divide and I get a 0.8. Just put that in your calculator. So I liked this one having an or problem where it's like prime given odd. It's just kind of a different way to think of it through a probability table. And you could make a probability table for almost every situation that you're given. So all right. So okay, so for let me see, if 60% females are, maybe I'll do one more of, I just like it when the wording, if I write out the wording a little bit different. Hi Autumn, we're just adding a couple problems on 8.3. So if 60% of a store's customers are female, 75% of the female customers have credit cards at the store, what's probability? So I'm gonna write, well, do we need that? 75. All right, so I'm going to write this one out, but it's okay. It's if 60%, this one's similar to one in your homework, but of a store, stores customers are female. Okay, and 75% of the female customers have a credit card. This is old because we all have credit cards. 75% of the females have credit cards. Okay, what's the probability that a customer selected at random is a female and has a store credit card? Oh, credit cards at that store. So, credit card at that store. So that makes it a little bit harder, right? Like you were walking into, Home Depot and you have a Home Depot credit card. That's what it's trying to get at. Okay, so what is the probability that you have a female, given they have the credit card? Okay, so that's the symbols for it. So not given, sorry. That you walk in and the female has a store credit card. So you have to be first female, and then you have to be having that credit card. So the probability of being a female is 60%. And means times. This is an and. Okay, so we're going to times that by the probability of having the credit card for that store is 75. Right, so that's going to end up with 0.445. So 45% of the people that walk in would be a female with a credit card for that specific store. Yeah. And if I was a male, I don't know. That's the only question that one asked, I guess. Okay, I thought that one we could do a given one on that, but I don't have enough information. So, okay, let's move on to the other section 8.4. So we had 8.3 and 8.4. Now 8.4 is very short and it kind of looks really hideous in the note packet. So I really want you, this is ugly. Okay. I really want you to think about if you set up a tree diagram, you're really going to times your row that you want together, those probabilities. And then if you have more than one row meets it, then you'll add those together. That's what this is trying to say. And it's super not pretty. So let's see. So this is their tree diagram that they drew. And they are saying for problem 1 here, they're like, okay, what is the probability of B given F? Okay, so what are they really asking for B given F? They're saying, where are B and F together? So let's write this out just so we have it. It's going to be, what's the probability of B and F divided by the probability of F. So the probability of F is a little bit harder than, just the probability of F. Okay, but that's the idea that we're looking for. So B given F. Okay, so if we go up here and we say B given F. So if we look at this, we have B is got the 0.5, right? And then out to F is got a 0.4. So the probability of B and then given F of B given F is timesing those two probabilities. That train is going to be times together. So we would have the 0.5 and the 0.4 for the top one. Oops, I just writing that weird. Okay, that's where they both are, and times them. Now for F, we're going to have more than one way to get F. This was the and idea here, but where are all the F's? We could be here, we could be here, right? and here. So we have to, for the bottom one, figure out all these probabilities. So this one is 0.1 times 0.1. This one's 0.5 times 0.4. This one is 0.4 times 0.2. We're just timesing that row. So times this one, then this one, and so forth. So let's calculate these out. So 0.4 times 0.2 is going to give me 0.08 on that row. And 0.5 times 0.4 is just going to give me a 0.2. 0.1 times 0.1 is 0.01. And those are the probability of, right? Because it's the whole row. So when we go to write this down here, we're going to have to write those three numbers added together. So 0.08 plus 0.2 plus 0.01. So we'll times the top, add the bottom, and I end up with 0.69. So those are tricky. Kind of like really we're timesing each tree diagram. So you only have 5 questions on this homework. One, you have to draw your own tree. The rest of the trees are all ready for you, and you're just really timesing through the tree. Okay, so for P or 2, sorry, it's probability of A given E. Okay, so we have A given E. So I'm going to erase what we have on here just so we can see. So A given E. So that's going to be this one. A given E is 0.4 times 0.6, which I'm just going to times together. So 0.4 times 0.6, and that's going to give me 0.24. And so that's where they both are, A given E. Okay, A given E. And then we need the probability of all E's because E was the second one. So this one would be 0.5 times 0.5. 0.5 times 0.5 is 0.0 or 0.25. And then 0.1 times 0.6 for this one. And that's 0.06. So those are the 3 E's. So we'll put the 0.24 on top, the and where they both are, over the 0.24 again, but we have to add it to the other 2 E ones, which were what, 0.25, and I can still see the 0.06 there. Okay, and then calculate that out, and they say 0.44. Hopefully they did it right. All right, I don't need to keep doing all the same. Do they show any other ones? Good. I was like, I don't want to keep doing the same one. I want to be able to like have a little bit different. The ball, probability of a red ball. This one. Well, this one might be harder than I even make you do. Okay, so a container has 8 red. Yeah, this is just too hard to do a tree with. 2 balls that are drawn in succession without replacement. If the ball is white, there's this one. If the ball is white, what's the probability that the first ball was red? You have 8 red, 5. This one's just harder than I'm going to give you. I don't even want to go over it. So, and then they had, and this one just keeps going. That's the only problems I think they had. The supply 19, maybe 19's easier to do. I think 19. So the reason why I don't like the red and ball ones, because I can't do a tree diagram with it, because there's freaking 12 of them. Be 12 and then 3 and then 5. I'm like, no, we don't want it. We need the numbers to be small. So an office supply company sells 3 different computer systems, ABC. Oh, we can do one. They sell 3 things, A, B, and C. 65% of the customers who buy a computer buy brand A. So 65% buy brand A. Okay. Um, 15% buy brand B and 20% buy brand C. So it gave me those probabilities. At the time of purchase, the customer is offered to extend the warranty for an added fee of 25% of the customer. Oh, for an added fee. The 25% of the customers who bought brand A, 40% did this extended warranty. So 65. So this is just the warranty. There's not two choices. It's like either warranty or not warranty, right? So not warranty. So the warranty was what, 25%? Customers who bought brand A. Yeah. 25% said, yeah, I'll take my extended warranty. That means 75% chose not to. So if they picked brand B, okay, so if they picked brand B, then 20% of the customers bought brand C. So 20% chose, yeah, I'd like a warranty, and 80% chose, no, thank you. And with brand C, they say, C. Oh, 40% for B. Sorry, 20% was this one. Not W was 80, and this one was 40%. So 40% said yes, so 60% said no, thank you. All right. If a customer brings a computer in for repair under their extended warranty, what's the probability that the computer was from brand A, blah, blah, blah. Okay. So we're really looking for the probability of A given they chose the extended warranty. Customer brings in a computer from the repair. What's the probability the computer was from brand A? So they had the warranty and brand A. So when we go to set this up, right, then we need where they both are, A and W. So that's going to be this row. That's going to be 0.65 times 0.25. Which, oh, what does that equal? I'm going to put this somewhere else. It's going to be in our way. So the probability of a given warranty. So we're going to have 0.65 times 0.25, which is 0.1625, right? So that's our numerator, because that's where they both are, A and warranty. And then we have to look at the denominator is going to have all the W's, right? Because you have to do all W's. You have to do all of the second one is your bottom. So we have the 0.1625. Now we have to then also add it to the other possibilities. So this one was 0.15 times 0.4. So 0.15 times 0.4 is going to give me 0.06. This next one is 0.2 times 0.2. Oops, 0.2 times 0.2 is 0.04. 0.04. Oh, that one's super small. Okay, so then the bottom will be plus this 0.06 plus this 0.04, and we get a total probability of about 61%. Okay, so we're really still doing that same idea, but we had to draw our own tree diagram for all the situations. So we're like, okay, we just had the 3, and then you just keep adding those probabilities. And these ones I had to come up with the not 2, and just these add to 1 for each branch there. Okay, and then we could do another one, but I think we're good. I think you can draw the tree. So really 8-3 is going to take you quite a bit of time. And you'll need to do those conditional probabilities in sort of like different situations. But the second one, I took out the super hard ones. I really wanted you to either have a tree and just times it across, or an easier tree like this one that you could create on your own. Okay, that's all I got for you today. I'm gonna stop my recording and then I can answer.